I think we are on section 7.3, right? About to derive the relationship between all the amplitudes. Right? We finished 7.37, right? And we're about to talk about the two cases. I mean, we probably need to, so let's rewrite. We derive this from the boundary condition. Remember that. These are still in vector form. So let's just copy them right now and give them number. Okay. So the first one. First one is this is from divergence D is 0. I mean, because there's no charge density. And this is E0 incident amplitude. E0 double point is the refracted amplitude for the electric field. And epsilon pi is in the upper medium. So E0 pi is the amplitude for the refracted wave. And N is just basically Z. It's the normal unit vector for the boundary between the two medium. This means jump. The square bracket means it's the one medium minus one medium at z equals 0. This is it. Remember we need the figure anyway. So the boundary is this is z axis. So you have z equals 0 is the boundary. This is epsilon mu. This is epsilon mu. Oh, let's draw again all the wave vector. This is k for the incident wave. Refracted wave is k double prime. The angle we already showed that they are the same, right? And then we have the refracted wave, k prime, and the angle is R, and it's R and I is related to with the Snell's law. We also divide that. Okay, so this is N, and it's a C basically. The second equation is this should be from the Faraday's law, because easier because magnetic field is related to because we need that relation later. So we'll figure that out. Minus. Unfortunately, just too many things to copy. But we need that because these are in vector forms, so not easy to use. The goal is to solve E pi and E double pi in terms of E. So the refracted and refracted amplitude in terms of the incident amplitude. Obviously, these are linear equations, so they are just proportional. So only the ratio is important. This one? This one? That's the, no, this one doesn't have the other one has the Ampere's law will have because Ampere's law is curl H. Curl H is positive D, positive T plus J. Defined B, we had a root mu epsilon. Well, you can use that. We can write it down right away. That's from the Faraday's law. Faraday's law. You have curl E is minus positive D, positive G. And everything is proportional to e to the I a dot x minus e to the t. right? So both E and B proportional to that for a plane wave. And so when you substitute this form into this, the relationship between this is basically the curl is you're pulling out an IK cos E. And partial T is you're pulling out minus I omega. Minus cancel becomes I omega. So that you cancel the I. So B is basically K cos E divided by omega. Omega is the same for always. So there's no, you don't need the mu. But what you're referring to is, if you want, you can use the phase velocity. You already know that the phase velocity omega over K. It's the phase velocity, and for a medium, for what we define the medium is epsilon. I mean, you can substitute, like you divide omega here, and the omega is just K divided by square root of mu epsilon. You can do that, and if you divide it by omega, and omega is K, you can change this to a unit vector K direction. And sometimes it's useful because this unit vector, when we talk about a plane wave, we define it as the n direction. It's different from this n, so the notation, there's some confusion in notation, but in the previous chapter, we defined that as the n vector. And there's a advantage sometimes to define this one. So instead of writing as K cos E, and so divide the omega is K, and then divided by, so you can see B is what to divide that K unit vector. You can do that, but in our case, we want to keep the wave vector, explicitly keep the K vector. I mean, we later might use that to express it. So there's a freedom you choose how you express your final result. But anyway, let's keep the form that Jackson used in here. This is 2, this is 3, the last one is, now this is from the Ampere's law, so it's H, so you divide it by mu. This is your double pi. And that is cos A. All right, so this derivation is actually pretty straightforward, but it's all algebra, no calculus. But no, it's just simultaneous equation. There's a lot of writing and tedious, but you just need to follow through. Okay, and now to solve E0 pi 0 double pi using this equation, these are in vector form, it's so a little complicated. We need to add this all entangled, so we need to disentangle all the vector to get this, and as might be too complicated to do it. Easier to do a component form, basically just separate it into two cases, just like Jackson here. So there are two graphs, two panel in 7.6, the figure. So A is one case and case one, and B is case two. The case one, so they basically represent two independent polarization, and we choose to use linear polarization. It turns out to be easier for this kind of medium. And if you use circular polarization, and they become coupled, and so it becomes difficult. At least for this medium, for some other medium, circular polarization might be easier. So, but for a medium, simply has a constant epsilon and mu, and that this is easier. And so we choose the two cases. The first case is with magnetic electric field in the y direction. So this is The board is the x direction, which is what we call the plane of incident, which means the K only has a vector along x and z on the z, so it doesn't have the y component. And that by matching the boundary condition, all these wave vector are also on the same plane. You don't have wave vector going out. Okay, so all ky's are 0 for all three wave vectors. So the first case is the electric field is in the y direction, perpendicular to the plane of incident. Let's see, this is the y direction is going in because of the right-hand rule. So electric field in here. So you have you can write that E0 is just E0 y, right? And as usual, you have this same phase vector. We might later just ignore this phase vector because just every quantity has this one, so you may ignore that later. Okay, so Jackson actually didn't have all the intermediate step, but we need to work that out to get to Jackson's equation. Okay, and now that's fine, and so then all these others are the same. So E0 prime, E0 prime, y, and then the same phase vector, and then likewise E0. This is the amplitude. So we define the scalar amplitude rather than vector. Because we define this in the y direction. And so there's a freedom to define this because we're just choosing everything in the y direction at right now, and then put the sign in this quantity. So if it turns out that it points to the opposite direction, then you will have a negative sign. Okay, this is just the definition. And it hasn't figured out, say, if this is positive, whether this is positive or negative. That needs to be solved. Okay, so now, but this will allow us to simplify this into instead of vector equation. For this case, you have relationship between all these scalar magnitudes. Okay, and now we just want to substitute all these to here. They need to satisfy all four equations, but then they're not independent. We'll basically finally get two equations out of it. Okay, and one equation is trivial because n is z, n is along z, these are y, right? Y dot c of this is 0, so this equation is not useful. Equation 1 is not useful. Okay, so that, but we still have three equations, and two equations will give you the same condition, and so finally you have two equations. All right, and see which one is easier to use. Right, the third one is without all the cos part. I mean, without all the k, this one might be easier, right? And everything is in y. This is in z, right? C hat. This is basically c hat. Y cos z is x, right? So everything has the x component, so you don't need to write out the x unit vector anyway. So basically, just the amplitude satisfy the same thing. So 3 trivial E0 plus E0 double pi equals E0. Yeah. Okay, so that's easy enough. And now the next one, we don't know which one we do. I mean, you just need to try. Okay, and so they both are actually both are very similar. So Maybe this one is without all the mu. Maybe this one is easier. And let's see what we should do. Why don't we? These are all triple product with the cos and dot product, right? And I think we could use the rotation. The cyclic. You cyclic the three terms one way or the other. If you just cyclic it, then it doesn't change sign. If you just interchange two of them, it change sign. Say if you consider this one cos and dot this one. If you just interchange this two, you change the sign. Obviously, if you interchange this two, then you change the sign. But you cyclic it through, it doesn't change. Okay, so like k cos E0 dot n, it would be similar to n cos E dot E, my n cos k dot E0 and n cos k dot E0, or which one will be easier? Maybe easy. This is E0. We want n cos E0, and maybe we want n cos E0. So move it together. See, try it. Okay, cos dot n. The cyclic rule will be we actually want n cos to, I mean, you can write down n cos k. This n moves to here, k moves to here, dot E0, and also equals to E0 cos n dot k. See which one is easier. And this is only in y direction. This is in z direction. So that would give you x. Maybe this one is easier. So this one will give you E0 is in the y direction. So you give you E0 y cos c is x dot into k. So that basically pick up a k sub x, the x component E0 k sub x, which is equals to E0 k. K in the x component is this angle is I, so it's sine. Okay, so basically we change to that. So let's use that to see if we get something independent. So this is that, so E0 k sine I. And similarly, this one will give you E0 double pi. And k double pi, the magnitude is still k because it's in the same medium. The component of x is still the same because the projection is the same. So actually, they both have a k sine I. So you might as well pick it. Take it out in E0 plus E0 double pi. Right, because they both have the same x component, which is sine, except the magnitude is different. So you just pull out k sine I. And but this one is now you need to change to k pi. So this is E0 pi k pi sine. Now this is sine R. Yeah. Okay. Right, so we got a two. These two are independent because obviously not the same. And k double pi is equals to k because it's in the same medium, right? You need to remember that. In the instant wave satisfy this one, the refracted wave is also satisfy the same. We have the same phase velocity, so therefore the wave number they are the same. Right. All right, that seems to be enough. And finally, you might want to double check this, whether this will give you independent solution. And that actually shouldn't be, because now this is a cross product. Instead of a dot product, you cannot use this rule. And the cross product, you can work out one of them. So, cos zero, cos n. Consider this cos in this. There are two terms. One is k dot n zero, and then minus k dot e zero. Not k dot, not it's e zero dot n. Dot n in the table. And e zero dot n is 0 in this case. And so it's just k dot n e zero. And k dot n is the z component. So it's and z, this is in the y direction. So everyone is in the y direction. And just give you the kz, k dot n is in the z components is cosine. That one will give you a cosine. Right. So k equals to k cosine I easy. And the other one will give you, I mean, you divide it by mu also. Divided by mu. And this one is actually the same. Let's see. K is omega multiplied square of mu epsilon, and then you divide it by epsilon over mu. I was trying to see whether this one will give you independent. So this should give you one of these two. And why didn't I get that? There's a cosine I for the t term in cosine. The boundary condition is k dot x is the same for all three, so it's k sine equals to k maybe this one is independent. I actually this one I take it back. So this one actually is not independent. So number two actually give you we repeat the equation. So k sine I is the same as k pi sine I. So this two cancel. As you see. So this one is actually exactly the same. 2 is exactly from 3. 3 and 2 will give you the same equation. So we actually need to work this out. So this is actually important. So it gives you a cosine I and k, and then we divide it by here. So you have k. And the first two terms, this is number 4. You have k divided by mu, the same two terms, and then E0. Let's see the cosine. the incident is the cosine I, this kc component. The k double prime is because it's propagating backward in z, so you actually minus cosine I. So you have a second term is have a minus sign and then multiply this one. Okay, and then the last term is k pi divided by u pi c pi. Okay, now that's more like it. Right. And see if Jackson has these two equations. 7.38. Yeah, this is basically what we have, except that Jackson already used this. K is omega, but omega is the same for this three, so K is proportional to square root mu over epsilon. So this divided by mu, so it's square root of epsilon over mu. So that is what Jackson has. So you can change this to square root of epsilon over mu. And likewise, this change to square root of epsilon pi over mu pi. Oh yeah, yes, there's a cosine. Thank you. It's a cosine R. Yeah, because of this, there's a cosine. So for this one, you end up have to see the C component also. All right. So after a while, so we finally get two equations, and the rest is just to solve these two simultaneous equations, which should be straightforward, except the form may be not that elegant, but it's not ugly, but it's just to solve it. So, and you have three quantities, but again, only the ratio is important. So you need to solve ECO prime divided by ECO, and then ECO double prime divided by ECO. Okay, so can we use this K? Your question is,
can we just cancel K cosine and K cosine like we cancel K sine A and K prime sine A?
Can we cancel K cosine and K prime cosine? You cannot do that because the equation is this one, not the cosine. This is what we match the boundary condition. How we match it. We need to match the boundary condition. All the phase has to be the same. So x k dot x equals k prime dot x prime. It doesn't change. X doesn't change. Equals to k dot x. And then k again. K is only in xz plane, right? And this is z. This is evaluated at z equals 0. X is basically just along x. So this is just k x equals to k prime x equals to k double prime. Right? Cancel the x, only the k, x component of the k the same. Right? That's the boundary condition, not the z component. You don't have the information of the z component. What you're talking about cosine will be the z component. Is that okay? Yeah. So you cannot cancel this. Phase difference?
Yeah, equal phase difference of plus pi by 2, so sine A becomes cos pi.
Well,
yeah, but
you cannot do that, right? You cannot do that, right? All the phase should be, I mean, these things all are in complex. So we haven't ignored the phase yet. We will keep all the phase actually later on. That's actually important. But these are complex number. They can have phase information. So I think up to here is general. Up to here is, I mean, this angle, we fix that by this condition. By this condition in the Snell's law. We'll later on apply the Snell's law later. But let's solve it first, and then finally the equation to write it in terms of the initial angle. We need to use the Snell's law because there's this R. We need to solve this R by the Snell's law anyway. Okay, and let's find a space to. I don't want to erase. I mean, maybe we can erase this because this is just work out the vector identity. So, is this? Let's see if we can have enough space to write out the solution. Okay. And now there's two equations. See what is easier. What do you think? Which is easier? We want to eliminate one of them. Let's see. It's easier pi, but why don't we put easier pi over here also and group easier double pi? I mean, either way is fine actually. Let's just write it this way. So you have a epsilon EC minus EC double pi cosine I equals to epsilon pi mu pi E0 pi. Now E0 pi becomes E0 plus E0 double pi cosine I. All right, so that makes the two sides a little symmetric. So we just need to group the E0 on one side and E0 double pi. We actually should move all the E0 double pi on one side, E0 on the other side, and divide E0. And the coefficient of that to the denominator, and that should solve the E0 double pi. So all we want is E0 double pi. Okay. I mean, either way is you just need to change the equation. So if we group the coefficient of E0, if we get in the numerator, say that should be this one, move this to this side, epsilon for mu cosine I, and then move it to there is minus epsilon pi for mu pi cosine I. And likewise, E0 double pi. This denominator is the coefficient E0 double pi. So you could move this to here. So now it's plus 3. Okay, so that's not too bad. And then finally, you just substitute E0 double pi over E0. So E0 pi over E0 is 1 plus E0 double pi over E0. Just use this one. It's basically just this 1 plus 1 plus 2. So the denominator will be the same. Right? Just basically common denominator is this one with the common denominator, this one. And the numerator is this one plus this one. So basically cancel this one because one is plus sign, the other is minus sign. And two of the first two. That should be the final answer. Right. This should be 7.39, except that Jackson now used the index of refraction and then also the Snell's law. Okay, and the index of refraction basically n. N is the phase velocity divided by the C divided by the phase, right? And so N should be basically C is phase velocity is this one, so mu C is 1 over mu 0 epsilon C. Right. Yeah, the same. So you can use the, so this one will be proportional to N divided by mu. I mean, all these are square root of epsilon over mu is N. So like this one is N divided by mu, right? N divided, because the denominator of epsilon 0, mu 0 is all cancelled between the numerator and denominator, so we don't need to keep that. So whenever you see the square of this thing, you should change that to say this is N divided by mu, this is N pi divided by mu pi. This is, again, all the terms are like that. So then you should recover. That what Jackson has. So N divided by mu, and then you multiply mu to the other term throughout the numerator and denominator. So you have mu over mu pi. And this is N, this is N, mu over mu pi. And finally, it's just the cosine R, using the Snell's law. Snell's law is N sine I equals to N pi sine R. The cosine R is square root of 1 minus sine square R, which is N square sine square R divided by N pi square. Right. And then this one you have N pi, so you multiply N pi N pi square minus N sine square. So this is the factor in what Jackson's expression. So again, with all these substitution with the index of refraction and then the Snell's law, you can check that these two are the same as 7.39. Is that okay? So it took a while. It took quite a long time to divide that. Okay.